Section 6.4, Day 3, trig proofs. Now, in a way, guys, although they give you some messier looking stuff, trig proofs are actually a little bit easier than the simplifying ones, because on the simplifying ones, we were kind of flying blind. They didn't tell us what we were trying to simplify it down to. We had to just go until we think we couldn't simplify it anymore. Sometimes that was really obvious, other times you kind of were left wondering if it could go farther. On trig proofs, you know exactly what you're headed towards. So for example, they may ask you to prove the following identity. What an identity is, guys, is it is an equation with a generic angle in it, A or theta or beta or alpha, and it's an equation that holds true for any angle. So it holds true for 30 degrees, it holds true for 40 degrees, it holds true for 52.7 degrees, it holds true for any angle. Okay? So, let's say they want us to prove that cosecant of A times tangent of A times cosine of A is equal to 1. Here's the key with proofs, guys. They are telling us that they're equal. They're not going to ask you to prove something that's not true. However, because they are asking us to prove that they are equal, you can only sorry, my pen's not working great today. Work with one side. You have to pick which side you're going to work with. Now, which side looks like it's easier to work with? The one. That's not the one you want to use. You want to choose the complicated side. The reason being, guys, there's an infinite number of ways to complicate something. By adding or subtracting or multiplying or dividing or whatever, there's a finite number of ways to simplify something. So you always want to take the complicated side and you want to simplify it. Otherwise, you're just asking for trouble. Okay? So always choose the complicated side. And if one doesn't seem any more complicated than the other, then just pick whichever one you want to work with. I'm going to change this into sine and cosine. So this is 1 over sine of A times sine of A over cosine of A times cosine of A. What then happens here? The sines cancel and the cosines cancel, which leaves us 1. This is what we were trying to prove. So you can just circle it and then connect it to the one you were trying to prove. But notice I only worked with the left side. That is extremely important. That is the overriding rule for trig proofs. You cannot work with both sides. You cannot multiply both sides by something. You cannot add or subtract something from both sides. You cannot divide both sides by something. You can't square both sides, because as soon as you do, if I take cosecant A, tangent A, cosine of A equals 1, and let's say I multiplied both sides by 2, I have now assumed that they are really equal. As soon as you assume they're equal, then your proof ceases to be a proof. Okay? If I assume that 2 is equal to 1, then can't I multiply both sides by 2? Doesn't that mean that 4 is equal to 2? Can't I add 1 to both sides and prove that 5 is equal to 3? Why not? I'm allowed to multiply both sides by 2. I'm allowed to add 1 to both sides. So why is 5 not equal to 3? Because 2 is not equal to 1. We assumed something that wasn't true to begin with. If you assume something that's not true, then no conclusions you draw from that assumption are going to be true. Does that make sense? We're starting with a false assumption. We do not know these are equal. Yes, they are. They're asking us to show how we know they are, but we cannot assume that they are, because as soon as we assume that they are, it's no longer a proof. You can only work with one side and manipulate it until it matches the other side. Does everybody get that? Other than that, do you see this is exactly what you did last night? It's just last night they told you to simplify this and they didn't tell you what it simplified to. You just went on your merry way until you got it down as simple as possible. Now we know what we're headed towards. We know to stop when we get to that, when we show it's equal to 1. Does that make sense to everybody? So do you see why I say these are actually a little bit easier? Because if you look at the side you're going to work with and then you look at the other side that you're aiming for, the side that you're aiming for can give you clues about what you want to do on the side you're working with. For example, if you have a bunch of sines and cosines floating around on the left, the one you're working with, and you see that what you're shooting for on the right has nothing but cosine in it, then what are you at some point going to need to get rid of on the left side? All the sines. So start looking for ways to either get sine squared so you can make them into 1 minus cosine squared, or look for ways where you can cancel the cosines out. That's the idea. Does that make sense, everybody? Other than that, the process is the same. You're only working with one side. Last night you were only working with one side. They just didn't tell you what the other side was. That's the only difference. Yes, sir. Micah?
If it were like an equation equals to cotangent, could you immediately put it into cosine over sine?
Well, you would know that if you were able to get it to cosine over sine, then you know your next step would be to make it cotangent, and then it would match what was up here, right? So you wouldn't change this into to cosine over sine. You just know in your head that that's what you're aiming for, because then you know how to finish it. Does that make sense?
Yeah.
Now, one thing you can technically do, guys, if you get totally stuck, is off to the side, you can kind of work by itself with the other side. And if you can get some step on this side to match some step on this side, then what you do to finish the proof here is you just reverse these steps going back up. Right? So if you had step 1, step 2, step 3, step 4, and you had step, 1, 2, 3, 4, 5 over here, this was step 6, then step 7 would be step 4 from here. And step 8 would be step 3 from here. And do you see how you could walk your way backwards that way? So that is an acceptable way to do it. Sometimes you can work towards the middle from both sides, but you're not actually working with both sides at the same time. You're just kind of working with the one side off on a separate sheet of paper just to give you a hint as to what you're looking for. And then you can reverse your steps to finish the proof. So sometimes if you get stuck, that's not a bad way to go. All right, questions about any of that? Okay. There are some more examples of proofs in the book, but again, it's the same thing we were doing last night. That's not really different. What I need to talk to you guys about is I need to talk to you guys quickly about Pythagorean identities. The main Pythagorean identity is cosine squared theta plus sine squared theta equals 1. This is our main Pythagorean identity. Why is it Pythagorean? Because this is really x squared plus y squared equals 1. And if you think about the triangle that we get from the unit circle, right? X is your cosine, y is your sine. The hypotenuse is 1, so a squared plus b squared equals c squared. That's where this is coming from. It's from the Pythagorean theorem. So it's called a Pythagorean identity. This is what I refer to as the mother of all identities. It's really just the mother of all Pythagorean identities. We've seen already that we can take this and subtract cosine squared from both sides. So we know that sine squared theta equals 1 minus cosine squared theta. So there's identity 1, there's identity 2. We could also subtract sine squared from both sides, which gives us cosine squared theta equals 1 minus sine squared theta. We've already talked about and used those. There are a bunch of other identities that you get from the main identity, though, and that's what I want to talk to you about today so that you can use them if you need to. First of all, if I take cosine squared plus sine squared equals 1, I can divide everything by cosine squared. Right? That's legal, right? Because we know they're equal. That becomes 1 plus tangent squared equals secant squared theta. There's identity number 4. Now, if I wanted to, guys, couldn't I subtract the 1 to the other side? So there's tangent squared theta equals secant squared theta minus 1. There's another identity. So if I see a secant squared minus 1, I can take it out and put tangent squared in its place. And vice versa when we're doing trig proofs or simplifying. Now, if I can do this with dividing everything by cosine squared, what else could I do? Divide everything by sine squared, right? So do you see how quickly you can rederive these if you ever forget them? I mean, how long did it take to derive those? This is cotangent squared plus 1 equals cosecant squared. That's identity 6. And then identity 7, you move the 1 to the other side and you get cotangent squared is equal to cosecant squared minus 1. There are 7 identities that are really just manipulations of the first one. So be on the lookout for these. Whenever you have a square trig function, there is some Pythagorean identity that you could use. Questions about that? Okay, time for the homework.